There are 225,000 kilometers of active railway track in the United States alone. Every mile of it sits on soft ground, not on concrete foundations poured to bedrock, not on steel piles driven to a load-bearing stratum. On crushed stone, on compacted earth, on subgrades that shift with temperature and moisture, and the passage of 10,000 tons of freight every week. The heaviest freight locomotives ever built, machines weighing more than 600 tons, transmitting forces to the rail that exceed 100,000 pounds per axle, roll across this ground daily, at speed, without sinking. The question of why they do not sink is not a simple question. It sounds like one. The answer that most people carry, that the track spreads the load, that the ballast distributes the pressure, that the engineering is straightforward, is correct in its broad outline and deeply incomplete in its details. The real answer involves soil mechanics that were not formalized as a discipline until the 1920s. Load distribution geometry that took engineers a century of field failures to understand correctly, and a maintenance system so continuous and so precisely calibrated that the track you see from a passenger window is, in a meaningful sense, not the same track that was there 6 months ago. The ground beneath a railway is not passive. It is an active participant in the structure's behavior, absorbing energy, redistributing stress, responding to water and temperature in ways that the track geometry above reflects with millimeter precision. When the ground fails, the failure is rarely dramatic. It is almost always slow, almost always detectable in advance, and almost always the result of a maintenance system that missed something it was designed to catch. Understanding why railway tracks do not sink requires understanding a structure that most people never see, maintained by a system that most people never think about, operating on principles that took the engineering profession most of the 20th century to fully articulate. The question begins not with a track, but with the ground. Soil is not a uniform material. Every geotechnical engineer who has spent time in the field will describe the same fundamental discovery. The ground that appears stable on the surface is below it a layered record of geological history. Clays and silts deposited by ancient water, sands and gravels left by glacial advance and retreat, organic materials compressed over millennia, and voids created by groundwater movement. The bearing capacity of this material, its ability to resist vertical load without deforming, varies by orders of magnitude across short distances and changes significantly with moisture content. The bearing capacity of saturated clay, measured in pounds per square foot, can be less than 1% of the bearing capacity of dense gravel under the same moisture conditions. A subgrade that carries train loads without measurable deflection in dry summer conditions can develop significant plastic deformation under the same loads in a wet spring, when the clay fraction of the soil has absorbed enough moisture to approach its liquid limit, the point at which soil transitions from a plastic solid to a viscous fluid. Early railway engineers working in the 1820s and 1830s, before soil mechanics existed as a formal discipline, encountered this variability empirically. The Liverpool and Manchester Railway, opened in 1830, crossed Chat Moss, a peat bog of exceptional depth and instability, using a technique that its engineer, George Stephenson, developed through trial and observation rather than calculation. Stephenson floated the railway on a raft of heather and brushwood, distributing the load of the track over a surface area large enough to reduce the pressure per unit area below the point at which the peat would fail. The technique worked, and the railway opened on schedule. What Stephenson could not have articulated, because the mathematical framework to articulate it did not exist, was that he had intuited the fundamental principle that all subsequent railway track engineering would refine. The problem of keeping a railway from sinking is a problem of pressure management. Not the absolute weight of the train, but the pressure that weight exerts on the ground beneath it. Pressure is force divided by area. A locomotive weighing 600 tons exerts enormous total force on the ground. But that force is distributed, first through the wheels to the rails, then through the rails to the sleepers, then through the sleepers to the ballast layer, and finally through the ballast to the subgrade. At each stage of this distribution, the area over which the force acts increases, and the pressure at the bottom of each layer is substantially lower than the pressure at the top. The mathematics of this distribution is not intuitive. The rail itself, a continuous beam supported at intervals by the sleepers beneath it, spreads each wheel load across multiple sleepers simultaneously. Not just the sleeper directly beneath the wheel, but several sleepers in each direction, each receiving a portion of the load that diminishes with distance from the point of application. The stiffness of the rail, measured by its cross-sectional moment of inertia, determines how effectively it performs this distribution function. A heavier rail, more steel per meter, distributes each wheel load across more sleepers. A lighter rail concentrates it more severely. This is why the standard rail section used in American heavy freight service, the 136-pound per yard section that has been the North American standard for mainline track since the 1970s, weighs nearly 3 times as much as the rail sections used on light industrial tracks. The difference in weight is not primarily about strength under a single wheel. It is primarily about the distribution area over which each wheel load is spread, and therefore about the pressure that arrives at the ballast surface beneath each sleeper. The sleeper, called a tie in American practice, a sleeper in British and Commonwealth practice, performs the next stage of distribution. A concrete sleeper in modern North American mainline track is typically 2.7 meters long and 0.28 meters wide, presenting a bearing area to the ballast beneath it that is approximately 10 times the footprint of the wheel flange above it. The transition from the focused contact of a steel wheel on a steel rail to the distributed bearing of a concrete sleeper on ballast represents a pressure reduction by a factor that depends on the specific geometry and the load distribution pattern of the rail above. The ballast layer performs the final distribution stage. Crushed stone, granite, limestone, or trap rock, each chosen for specific hardness and drainage characteristics, receives the pressure from the sleepers and distributes it further into the subgrade below. The angle of this distribution, which geotechnical engineers call the load spread angle, depends on the particle size, the degree of compaction, and the depth of the ballast layer. Standard North American mainline practice specifies a minimum ballast depth of 12 inches beneath the base of the sleeper. Heavy haul coal routes, where the cumulative loading is severe, routinely use 18 to 24 inches. At the base of this system, at the contact surface between the ballast and the natural subgrade, the pressure from a loaded freight locomotive, which began as a contact stress of several 100,000 pounds per square foot between wheel and rail, has been reduced to a few pounds per square foot, a level that most natural subgrades can support indefinitely without measurable deformation. The structure works when it is maintained correctly, and when the subgrade performs as designed. It works with a reliability that the 6 million daily train movements on the American network demonstrate. The question is, what happens when any element of the system deviates from its designed condition? The ballast is the most visually prominent component of the track structure and, in practice, the most maintenance-intensive. Its function depends on properties that deteriorate progressively with use. The angular shape of its particles, which provides the interlock resistance that gives the ballast its load-bearing capacity. Its drainage characteristics, which keep the subgrade from becoming saturated. And its depth, which determines the load distribution geometry that the pressure calculations depend on. Each train movement subjects the ballast to cyclic loading, a rapid application and release of force as each axle passes. Under this cyclic loading, two degradation processes occur simultaneously. The angular particles of freshly placed ballast, which interlock under load to create a stable matrix, progressively fracture at their contact points, producing fine particles that fill the voids between the larger stones. As the void ratio of the ballast decreases, its drainage capacity falls. Water that should pass quickly through the ballast layer begins to pond. Saturated ballast transmits load differently than drained ballast. The poor water pressure that develops under cyclic loading can temporarily reduce the effective stress between particles, allowing plastic deformation that would not occur in drained conditions. Simultaneously, fine material from the subgrade migrates upward into the ballast through the repeated pumping action of cyclic loading, a phenomenon that engineers call ballast fouling from subgrade intrusion. On routes where the subgrade contains a significant clay fraction, this upward migration can deliver several centimeters of fine material per year into the base of the ballast layer. The material accumulates, further reducing drainage, further increasing the susceptibility to poor pressure development under load. The track geometry that results from these processes is not a uniform settlement. It is a differentiated deformation, different rates of deterioration at different locations along the track, producing the characteristic surface irregularities that railway engineers call top, cross-level, alignment, and gauge deviations. A track that has developed significant geometry irregularities transmits dynamic forces to the subgrade that are substantially higher than the static forces that the pressure distribution calculations predict. The wheel that hits a low point in the rail profile does not simply apply the static wheel load. It applies a static load multiplied by a dynamic amplification factor that depends on the speed of the train and the severity and wavelength of the geometry deviation. This dynamic amplification is the mechanism by which track geometry deterioration becomes self-accelerating. A small deviation creates higher dynamic loading. Higher dynamic loading produces faster ballast degradation. Faster ballast degradation produces larger deviations. The process compounds until intervention, maintenance, resets the geometry and the load distribution back to designed conditions. The maintenance system that keeps this process from running to failure is the least visible and most continuous engineering operation in the transportation infrastructure. Track geometry measurement cars, specialized vehicles equipped with inertial measurement systems, laser profilometers, and GPS positioning, traverse every mile of mainline track on a schedule determined by the traffic density and the historical rate of geometry deterioration on each segment. On the heaviest trafficked American main lines, geometry measurement is conducted monthly. The data produced by each measurement run is compared against the previous run and against the progressive trend over multiple measurement cycles to identify segments where deterioration is accelerating. The intervention that follows a geometry measurement is, in most cases, not a track replacement. It is a tamping operation, a process in which a specialized machine called a tamper inserts vibrating tines into the ballast beneath each sleeper and compacts the material to restore the designed bearing geometry. A modern hydraulic tamper can process several hundred sleepers per hour, lifting the track to its design profile, consolidating the ballast beneath each sleeper, and leaving a geometry that a post-tamping measurement car will confirm meets the tolerance specifications. The tamping operation does not address ballast fouling. It addresses geometry by repositioning existing material. When the ballast fouling index, a measure of the fine content in the ballast by weight, exceeds the threshold at which tamping can restore acceptable geometry for a useful service interval, the intervention required is undercutting, a machine that excavates the ballast to its full depth, screens out the fine material, and returns the cleaned ballast to the track. On heavily fouled sections, undercutting is followed by the addition of new clean ballast to restore the design depth and drainage characteristics. On segments where the subgrade itself has failed, where the bearing capacity has been reduced to the point where the load distribution geometry is insufficient regardless of the ballast condition, the intervention required is subgrade stabilization, excavation of the failed material and replacement with engineered fill, installation of geosynthetic separation layers to prevent future clay intrusion, or injection of stabilizing grouts into the subgrade. These operations are expensive, disruptive to train operations, and relatively infrequent on well-maintained main lines, but they occur on every railroad system in the world, on segments where the original construction encountered conditions that were not adequately characterized, or where drainage systems have failed over decades of service. The failure modes that produce visible track problems, the sudden subsidence, the dramatic geometry deviation that forces speed restrictions, are almost always the end state of a process that was detectable long before the visible failure occurred. The maintenance system exists to intercept that process before it reaches the visible stage. When it fails to intercept, when the measurement interval was too long, or the intervention was delayed by budget constraints or operational pressure, or the deterioration rate accelerated faster than the historical trend predicted, the result is a speed restriction. A section of track is flagged for reduced speed, which reduces the dynamic loading on the deteriorated geometry and buys the time needed to schedule and execute the required intervention. The American freight railroad system imposes speed restrictions on approximately 3 to 5% of its mainline mileage at any given time. This figure is not a failure metric. It is an operational parameter, the steady-state level of maintenance in progress that a system of this scale, handling this traffic volume, produces as a normal consequence of the degradation processes that no amount of maintenance funding entirely eliminates. The public experience of this system is the smoothness of the train ride, the absence of visible track deformation, the fact that freight trains weighing thousands of tons cross bridges and embankments and former swamps and river floodplains without the surface showing any evidence of the forces being applied to it. This experience is not an accident. It is the product of measurement, intervention, and the continuous recalibration of a structure that is simultaneously degrading and being restored. A process that has no beginning and no end. Only the ongoing equilibrium between deterioration and maintenance that defines every large infrastructure system that humans have built and chosen to maintain. The subgrade failure that most dramatically illustrates what this system prevents and what happens when it fails is not the sudden collapse. It is the progressive settlement that develops over months or years beneath a section of track where drainage has failed, where clay has migrated into the ballast, where the bearing capacity has been quietly diminishing while the track geometry has been deteriorating in increments too small to trigger immediate intervention. The Union Pacific's Feather River Canyon route in California provides one documented case study among many. The route traverses terrain where the subgrade consists of decomposed granite, a material that behaves as a competent bearing surface when dry and as a nearly cohesionless slurry when saturated. The drainage structures that keep this material dry require continuous maintenance. When a culvert fails or a drainage channel becomes blocked, the sequence that follows is predictable. Subgrade saturation, bearing capacity reduction, increased dynamic loading from geometry deterioration, accelerated fouling, and ultimately a settlement that requires excavation and reconstruction rather than tamping. The interval between the drainage failure and the visible track problem can be months. The maintenance system's value is measured in how consistently it detects the drainage failure before the subgrade saturation progresses to geometry deterioration, not in how efficiently it repairs the geometry after the deterioration has occurred. This is the engineering reality beneath the smooth ride. Not a static structure holding the load, a dynamic system, continuously detecting and responding to the degradation that the load produces. The 225,000 kilometers of track that does not sink is not track that was built to never sink. It is track that is maintained to be raised before it sinks far enough to matter. George Stephenson, floating his railway across Chat Moss on a raft of heather and brushwood in 1829, had no framework for calculating the bearing pressure his track imposed on the peat below. He had no soil mechanics, no pressure distribution theory, no geometry measurement car. He had observation, persistence, and the empirical intuition that spreading the load over a larger area would solve the problem that concentrated loading had created. He was right, and the principle he applied intuitively is the same principle that the 136-pound rail, the concrete sleeper, the compacted ballast layer, and the engineered subgrade preparation of a modern mainline track express in calculated, documented, inspected form. The sophistication has increased by orders of magnitude. The principle has not changed. What has changed is the understanding of how precisely the principle must be applied, how continuously the application must be monitored, and how quickly the system will deteriorate if the monitoring is interrupted. Stephenson's Chat Moss crossing required maintenance. The peat settled unevenly. The brushwood raft required reinforcement. The drainage demanded constant attention. The maintenance principles that kept his railway above the bog are the same principles that keep 225,000 kilometers of mainline track above the ground today. The ground is soft. The loads are enormous. The track does not sink. The reason is not the strength of the materials. It is the continuity of the attention.